morning, good people. My name is Mr. SEKGOTA, a lecturer at Gangala Tvet College, Middleburg campus. Today we are going to be discussing power machines and 5. The topic that we're going to be covering today is compressors. In this, we're going to divide it into 4 sections. We're going to start by explaining the machine, and then we follow by the functions of the compressor, and then we discuss the formulas related, and then later solve the calculation problems. What is a compressor? A compressor is a mechanical device that increases the pressure of a gas by reducing its volume. We've got different types of these compressors. Here below we've got types of compressors that we're going to be discussing today. Air compressors fall into distinct types. There are important differences in the fundamental behavior of the 2 types: the reciprocating compressor and the rotary compressor, of which sometimes is called the centrifugal compressor. The main function of the compressor. The function of an air compressor is to take a definite quantity of fluid, usually a gas and most often air, and deliver it at a required pressure. The most efficient machine will accomplish this with a minimum input of mechanical work. The 2 main types of compressors, which are the reciprocating compressor and the rotary compressor. They are different, however, in performance. So the difference of the 2 types based on performance is that the reciprocating compressor has the characteristics of low mass rate of flow and high pressure ratios, whereas the rotary compressor has a high mass rate of flow and low pressure ratios. The work done by a single stage compressor is shown below. When air is supplied to a compressor or is being sucked by the compressor, it compresses the air through with this polytropic compression with a certain index of expansion. Usually it will be given in it's notated as n. So this is called a constant, meaning that if these are condition 1 and 2, and then we're going to be expanding this, and then we cause a cycle, we will have conditions again here. Usually we'll see as we continue with the other exercises. So this expansion or compression, it is usually a polytropic, which is a constant, which will help you to have the conditions at 1 and conditions at 2, which can be equated to solve the unknowns. Here is the formula that you can use to calculate the work done. And if you can recall from the previous discussion in the thermodynamics of gases, we attained this formula where here we will be talking about the characteristics of a perfect gas, where we've got the mass in a certain gas constant that's behaving at a certain temperature. And then now, if you see P, which is pressure, volume, and temperature combined, this basically shows us that they're still continuing with the Charles and the Boyle's law combined together. So we can still use it in compressors because compressors mainly work on gases. So this will be the work done. This is the MRT formula from the previous. You can substitute this by that. If you can equate P1 V1 with MRT1, then you can replace or substitute P1 V1 with MRT. It will depend on what you have. So if you are given the temperature and the mass of the gas, you can use this to calculate the work done. And then if you've got the pressure and the volume, you can use this together with the index of compression. Here we've got the formulas that we're going to be using in the calculations involved in this section. If you are required to calculate the work done, these are the formulas you're going to use. With the help of this knowledge of the relationship between the pressure, the volume, and temperature, if you are required to calculate the power, this is the formula you can use. And then if you are required to calculate the efficiency, this is the formula. These are the formulas, however, you can use. Here we are given the problem statement, which I want us to quickly solve it and see how we're going to approach the compressor related questions. A single stage, single acting reciprocating air compressor has a bore of 210 millimeters and a stroke of 290 millimeters. It runs at a speed of 550 revs per minute. The clearance volume is 6% of the swept volume, and the cycles are polytropic throughout. At the intake point, the conditions are as follows: 97 kPa and 19 degrees Celsius. These are the conditions at the inlet or the intake, and the compression pressure is 600 kPa. This is the delivery pressure. And then they said the cycles are polytropic throughout. Then it means compression and expansion index is 1.35. So the first question says, determine the free air delivery in meter cube per minute. The free air conditions being 101.325 kPa and 15 degrees Celsius. If you check this pressure, it is atmospheric pressure. This is the atmospheric temperature, which is 15 degrees Celsius. So let's quickly solve this. Number A, we're going to be determining the free air flow delivery. Before solving every problem related to compressors, I would advise that we all the time draw the diagram that will explain the problem statement in terms of the diagram, in terms of the diagram where you're going to be drawing a PV diagram, because it helps you to actually see what's happening there. If you check here, in the previous slide, we spoke about the compression and the expansion, which is a constant. Now you can see where this takes effect. If you check here from point 1, point 2, this is where compression takes place. From 2 to 3, the pressure is constant. However, the volume still reduces. And then from 3 to 4, this expansion that is taking place. And then when we get to point 4, we're going back to 1, and then the pressure is constant. So with this, you are able to imagine what is happening inside the compressor. So you will be able to solve the related questions. So please pay attention to that. Always draw the diagram based on the information given from the problem statement. So the first thing we'll do, we'll find the soft volume. We're given the diameter, so we're going to use the area. You know that to get our volume is the area times the distance or the length. So we're given G, which was 210 millimeters. We're given the stroke length, which is 290 millimeters. So if we substitute this, we're going to get our soft volume. So soft volume is from here to here. Let me show you with the highlighter. So we were sweeping from here, point 1, we went all the way 2, 3. Hence why you see our short volume is V1 minus V3. So finding the short volume, we're going to substitute this, then this becomes V1 minus V3. We're going to do it in terms of V's. Then finding the clearance volume. Remember, the statement said to us that we've got the clearance volume is 6% of the short volume. So we're gonna say what we found, the short volume times 0.6 will give us the clearance volume. Clearance volume is from here to here. Usually it's notated with 3. That's why you see it here as V3. So here V1 is the total volume here. It's going to be the short volume plus the clearance volume. So it's the entire volume here, which is V1. It's going to be short volume plus the clearance volume, which is 0.1. We got it from here, 0.01 rather, and then plus 0.006, which we got it here. So our V1 now becomes the sum of the two, which is 0.0106 meter cubed. When we go to V4, the end of our compression, rather at the end of our expansion, that is the end of expansion, which is V4, where the pressure now becomes constant until we now complete the cycle. Remember guys, a cycle is the completion of those lines joined together from point 1 to point 1 again through 2, 3, 4 and 1 again. This completes a cycle. So get our V4 in terms of the pressure. For pressure 3, for pressure 2 is given. So now you can use V3, which you got from the previous question. Here is how you get your V4. So then the effective sub volume will be the one that is the sub volume is from here to here. That is effective. We're going to minus the V1. It's V1 minus V4. So this will be the effective sub volume. And the sub volume will be 0.0828 meter cube. Then now the question asks us to find the free air delivery cycle. Free air delivery. So the air that is delivered based on the atmospheric condition. So because of the relationship between the PVs, we're gonna say we will notate our free deliveries as F. Then we take the conditions at 1. So it will be PF times VF over TF, which is again P1 times V1 over T1. Now I'm going to call it V1 because now how we got our V1, it was the effective sub volume, which if you check here it's 1, I would call it V1, but actually the swept volume from the previous calculation. This is the reason why we had to calculate this. We wanted the effective swept volume, which is in terms of the difference between volume 1 and volume 4 completing the cycle. So we were given the conditions at atmospheric, and then we've got the conditions that are given when we are initially starting. It was 67 kPa at 19 degrees, and the conditions at atmospheric, it's 101.23. So here is how you convert from degrees Celsius to Kelvins. We're going to say 15 degrees plus 273, and it's going to become 288 Kelvin. 19 degrees plus 273, and will convert your degrees Celsius to Kelvin. It's 292. Then you just go and substitute here You're making the free, remember we're looking for free air delivery in terms of the volume per cycle. So what we'll do here, we're going to make V the subject of the formula, multiply T by this, and then we're going to divide by QF, then you will be left with VF. Now with this you can directly substitute all the values given. P1 was given at 97 kPa. The effective swept volume is 0.00828 times the temperature at the atmospheric conditions. It was 28 over the atmospheric pressure times the initial temperature in terms of Kelvin. Then you find it to be 0.0078 meter cubed. Now the free air delivery, remember they said per minute. This statement per minute. So we were also given the rotation per minute there. That was important. Let's just quickly go back to remember we were given the run or the speed per minute. So we're gonna say that volume that we got, you multiply it by the run per minute. The volume you got times that revolutions per minute, then you're gonna get yourself the free air delivery as 4.29 meter cube per minute. Just copy down the steps. That was how we solve A. So this is how we find free air delivery. The second question says, calculate the volumetric efficiency referred to the free air condition. So we'll solve it. Finding the volumetric efficiency, you're going to use it in terms of the volumes. We were able to calculate, remember from question 1, we were able to calculate the effective soft volume. Also calculated V1 minus V2, V3 rather. So this is what we got. We're going to multiply everything by 100% to get efficiency. So this is the volumetric efficiency, the ratio of the volume times 100. And you get yourself the volumetric efficiency. This was straightforward. Let's take the formula. Number C says calculate the air delivery temperature. So here we are looking for the air delivery temperature. So to solve this question, we are going to have to select a suitable formula first. So we go to our formulas and then we look at it. Then here, which formula can help us? So we're going to select this formula here because we know we've got the temperature, 1, but pressure ratios, the index of expansion. So we are looking for the delivery temperature. So this is how we do it. You come with your formula here, you make T2 the subject of the formula, then you substitute with the value of T1 which you got, and then we were given the pressure ratios, the index of expansion which was 1.35, then you get yourself your temperature, delivery in terms of kelvins. So if you want to convert it to degrees Celsius, you're going to say 468.33, and then you minus the 273, which is going to be 195.33 degrees Celsius. So this is how you get the delivery temperature. And then the last question, number D, says calculate the cycle power. So calculating the cycle power, we're first going to select a suitable formula. The actual power, we're going to use this formula. Then we substitute the values that we have. This is how we do it. After calculating everything, then we can just come here and substitute all the values. We were given the index of compression and expansion. We've got pressure 1, we've got soft volume, we've got pressure ratios, and then we multiply throughout. Then this should give us the power. If you pay attention here, let me highlight this for you so you can see. They said the cycle power. So that this formula here, the formula, this formula for power, if you check here, it says the actual power. This is the actual power, but the question requested us to calculate the cycle power. So pay attention to that. The cycle power, it means power per minute or per a cycle completed. If you check here, they multiplied by that revolutions per minute, which was 500 per minute, and we know that a minute has got 60 seconds. So you would say the actual power times the rev per minute, then this will give you the entire cycle power, which is 1559 kilowatts. So this is how you solve a single stage air compressor related problem. Let's quickly go back to the question. So you can copy down the question, work it out on the paper again, see if you are able to understand this without seeing the solution, and then refer to the solutions when you're done, so you can evaluate yourself in terms of understanding the compressor volumes. Remember, one important thing to do, always draw the diagram. Always start with the diagram so that you can have a scenario of what is required of you, or what is the relationship between the conditions, the pressure and the volumes. Then you can easily approach the calculations with the understanding of the diagram. I will end it here for today. Thank you very much for watching.